Okay, so let's start. So the next talk is called Advances in Algorithmic Recourse, Ensuring Causal Consistency, Fairness, and Robustness. And our speaker today is Professor Amir Hossein Karimi, who is an assistant professor at the University of Waterloo. So he's a professor in the Electrical Computer Engineering Department at the University of Waterloo, where he leads collaborative human AI reasoning machines lab. The lab mission is to advance the state of the art in AI and chart the path for trustworthy human AI symbiosis. Amir Hossein's research contributions have been showcased at various esteemed AI/ML-related platforms such as NeuroIPS. Before joining the University of Waterloo, Amir Hossein gained extensive industry experience at Meta, Google Brain, and DeepMind, and offered AI consulting services worth over $250,000 to numerous startups and incubators. Welcome, join me in welcoming Professor Amir Hossein Karimi.
Okay, well, thank you for that very warm welcome, and thank you all for coming during lunch hour. I know you might have preferred to be elsewhere, but I hope at least you take away something from the talk that makes your time worthwhile. So, can you hear me in the back, by the way? Back row? Hands up? Good. Yes, the doors are closing, so you might hear me better now. Awesome. Yes, so the advertised talk title is a bit different than this one here. I promise we'll get to the recourse part as well. But allow me to give you a bit of a prelude to why we're talking about recourse and what recourse is. So as we all know, in recent years, advances in AI has touched various industries, from healthcare to transportation to finance and education. And as the human dependency on these AI systems increases, so has the boundary between human and AI decision-making become increasingly blurred. Let's draw an analogy. Every one of us have in our home a series of machines which enable us to offload our physical labor to those machines. We interact with them insofar as we give them a predefined task. We trust that after some amount of processing or computation, they return an expected result. And all the while, they operate safely within predefined bounds of operation. If anything goes wrong, they beep at us, they blink at us, they have a user manual, they tell us what went wrong. It's not hard to imagine a future, perhaps even a today, where we have complementary systems that enable us to offload our cognitively laborious tasks to these systems. Which begs the question, what could go wrong? So, if we have systems such as ChatGPT or one of its APIs making consequential decisions for humans, and if they confidently give you a wrong answer, you should be able to query its representation, challenge its reasoning, correct its answer, and all the while communicate in a shared language substrate. And my argument today is that besides there being a need or a hunger by large companies to develop even more larger and more performant model, there's also a subtle but very much growing need to develop additional tools, systems, processes, and algorithms that can help us detect potential issues, correct problems and suggest alternatives, and also ultimately perfect the human-AI relationship. And broadly speaking, these three objectives are what make up the objectives of the CHARM lab at Waterloo, the Collaborative Human-AI Reasoning Machines lab. And a bit more technically speaking, we tackle the following research questions. The first one is, in the detect phase, how does one assay the safety, factuality, and ethics of AI systems to foster trust in AI? 2, how does one recover from or overturn poor experiences via decisions made by AI? And 3, how does one design systems that make use of the best of both human and machine abilities? Today's talk is going to focus on number 2, which we'll call algorithmic recourse. But before that, let me just say that addressing this agenda, of course, is going to require us to borrow tools and insights from a broad range of subfields of AI, including explainable AI, which aims to answer why questions and promote a conversation about a system's predictions; program synthesis, which allows for the discovery of models using non-code specifications that can be understood and commanded by a larger population; and finally, causal inference, which presents the beautiful mathematical framework allowing us to ground all of these methods in that framework. It's also a model for human cognition. Of course, this agenda goes far beyond AI as well, and we'd need expertise from across disciplines, including folks from multi-agent systems, psychology and cognitive science, as well as behavioral economics. So this prelude is also an open call for collaboration. If anyone has any interest in any of these fields here, I'm happy to chat, and I'm here after the talk as well. Okay, as promised, let's get on with the main topic today, which is algorithmic recourse. What I'll be presenting in the next half hour is the work done over the past half decade with a lot of excellent collaborators from across Europe. So what is algorithmic recourse? Let's start with a case study. This is Edward. He's 28. He is a software engineer. He's single. He has a salary of $75,000. He's managed to somehow save up $25,000, probably before inflation. And he's looking to purchase a home, probably not in Canada. So Edward, after months of scrupulous savings and many open house viewings, he's finally found a home that he's interested in, but in order to purchase it, he must first visit the bank. Now, the bank may use a model such as this one to decide whether or not Edward gets the loan. Does he get the loan here? Who thinks yes? Who thinks no? Good. He doesn't get the loan here. Or the bank may use this model, or perhaps one like this. And typically, as these models become more complex, they're better able to detect the nuances in the historical data sets, but they lose out on something important, which is their interpretability. We'll define that in a couple slides. In this context, of course, it's not just Edward, but there are other stakeholders, such as the bank may ask, such as RBC in this case, may ask, what are the most influential features towards a decision? A governing body or regulator may ask, is the system fair by relying on sensitive attributes such as age and marital status? And folks like Edward who didn't get the loan may ask, why not, and what should I do the next time I apply? Answering these questions broadly falls under the umbrella of explainable AI or interpretable ML, depending on which acronym you like, which is the ability to explain or to present in understandable terms to a human. XAI has two broad goals. The first one being to understand why a particular decision is output, and two, to recommend actions that would result in a desired output. Now, one method in the past few years that's attempted to address these questions is called counterfactual explanations, which are statements of the form how the world would have had to be different for that desired outcome to occur. In this case, they'd say to Edward, if your salary had been 100 grand instead of 75, you would have been offered the loan. Let's take a closer look at counterfactual explanations and see whether they actually address the needs of XAI. So here's Edward again. Might not be so clear. Oh, actually not on this slide. Anyways, here's Edward. Collectively, his features are represented as x of f, standing for x factual. He's at time t0, which we're using to evaluate his situation, and he's denied a loan. So y in this case is the prediction from the model. It's 0. Looking back in time, there exists a hypothetical Edward with some alternative combination of features, such as an increased salary, that would be offered the loan. So his prediction on that same system would be 1 minus y. Assuming the world is stationary and the model used by the bank remains stable, projecting forward in time, we'd get the same individual with the same set of features to be offered the loan. Now, I want to remind something. There's something missing from this picture, so let's go back to the definition of explanations and remind that one of the primary objectives of explanations is to act as a means to help a data subject act rather than merely understand. And so the missing link here is that arrow over there, which we call recourse, which are the actions required for the systematic process of reversing unfavorable decisions across a range of counterfactual scenarios. Intuitively, what this means is that counterfactual explanations might tell Edward where he needs to be, but not how to get there. And that is the primary objective of recourse. By the way, questions are welcome at any time, and there's a big light in my face, so just shout at me if I don't see your hand. Okay, so let's take a closer look at Edward. Now he's standing on a red dot. We have an arbitrary decision boundary represented by h theta. He's denied a loan. In 2017, the problem of counterfactual explanations was formulated by Wachter et al. As this optimization problem here. It's basically an argument over some distance or objective function such that the prediction of the model is flipped to some alternative decision. What that means visually is that if Edward is here, then the counterfactual explanations would put him on the other side of the decision boundary, either at this point or the one way up top. Now, there is an additional constraint in this optimization problem called the plausibility constraint, which says the alternative individual should make sense according to the distribution of the population. For instance, we can't recommend that Edward have negative age because we humans do not have negative age. That's an implausible part of the human population distribution. A couple years later, this optimization problem was reformulated, now by Hossein et al., which is almost the same optimization problem, but now in addition to there being a plausibility constraint on the second to last line, there's also now a feasibility constraint. So in that previous example, if Edward is 28, of course 25-year-olds would be completely plausible, but Edward can't reduce his age. So now this optimization problem, which gives almost identical results, allows us to incorporate more structure from the world in terms of the constraints that Edward or any individual can actually exert. And what that means is that now we're focusing on finding the minimal costly shifts, or these deltas or delta stars, that would put Edward on the other side of the decision boundary. Okay, so the questions that we try to address are, do counterfactual-based recourse actions from methods like Hossein et al. Yield optimal and feasible real-world actions for recourse, and how does providing recourse affect other stakeholders? The first question is, do counterfactual-based recourse actions from existing methods give us optimal and feasible real-world actions for recourse? In order to give actionable recommendations to individuals, we need to understand that any action we perform in a world has consequences. And how do we model that? We model that using the framework of causality. So let's do a bit of a brief background on causality. We adopt the structural causal model framework of Pearl. Who's heard of Pearl before? Good, some people in the audience. We'll try to catch everyone up. So the SCM framework says that a causal model M is made up of two parts. S, which is a set of structural equations which determine how, let's see if this works. So M is made up of two parts. S, which are the set of structural equations which determine how every variable x of r is a function of its parents as well as some background variables. And also the second part of the model M is a distribution over background variables. Okay, this is all a bit abstract. What do we mean? If you're going to take just one thing away from this talk, is that the field of causal inference and causality in general is a game of assumptions. What that means is that we always define variables x1, x2, and x3, such as age and marital status and bank balance, and that is the system that we're trying to study. Everything else about the system, such as inflation, COVID, all that, we abstract away from the system. And then what we're trying to do is we're trying to infer effects of changing one variable on the rest of the system. So one of the additional assumptions we make in order to actually make causal inference possible is that the corresponding causal graphical model for the causal system is acyclic, meaning that they have no cycles. And secondly, that as you can see, there are no links between the background variables u1, u2, and u3, and this is also a common assumption within causality, otherwise known as no hidden confounding. These two are very common assumptions in order to make any inferences about causal systems. Now, structural causal models entail three types of distributions, and in machine learning we typically only deal with one, but I'll explain a bit further. The distributions are, one, an observational distribution, two, interventional distributions, and three, counterfactual distributions. What does this mean? So an observational distribution is if I took a camera and I just observed the demographic in this room, what does the distribution look like? Interventional distribution would say, we'll answer queries like what would happen if? So what would happen if I advertised my talk to a particular demographic prior to the talk? What would then the distribution look like? Finally, counterfactual is, you've all now come to the talk, there is some demographic in the system, I've observed something about the system. What would have happened if I had done something else prior to the talk? What would the distribution look like? So these three distributions, which again in machine learning we only deal with the observational one, but causality and structural causal model frameworks allow us to go beyond these three, can otherwise be seen to lie on what's called a causal ladder, a ladder of causation. And these correspond to, as Pearl says, these correspond to different means of thinking. So the first observational distributions are observing the world, interventional distributions are acting on the world, and counterfactual distributions are imagining alternatives about the world. Or alternatively, as my supervisor from Germany puts it, we typically in machine learning deal with just the observational distribution, and we're trying to learn P of X. All of the generative models that you see, DALL-E, ChatGPT, all they do really is just learn this. But if we make further assumptions about the world and how causality works, then we can have access to alternative worlds. Alternative worlds are represented by the hammers on top. So if I act on the world, what would then happen? If I administer this drug to the population, what would happen? We can't answer these without making additional assumptions. Okay, so now with this side note aside, let's go back to the problem of recourse and try to wrap it up as to why we are talking about causality in the first place. So this is Edward again. I've brought in the numbers from the initial case study. Edward has a salary of 75 grand. He's saved up 25,000. I've now added some numbers to h theta, which was our classification model. Our decision boundary is sine of x1 plus 5x2 minus some threshold. And additionally, I've made some causal assumptions. Typically, people that are home seekers will save a portion of their salary towards their bank balance. In this case, I'm saying that 30% of Edward's income goes to some savings account used later for the down payment, let's say. The causal model representing the system on the left-hand side can be also visualized in the graph on the right. Now, existing methods that don't employ causality would give us either of the solutions that we see here. So they would give either delta or delta star. In the case, they would say somehow increase your salary by 25,000, which is a relative 33% increase in effort for Edward. Alternatively, they might say find a way to save an additional 5,000, maybe borrow from friends or family or do something. That's a 20% increase in effort. But obviously, they ignore any causal relations between the variables. So it's not hard to come up with an example whereby if Edward increases x1, his salary, by just 14%, of course, lower effort is better, then together, at the end of the year, what would happen is not only does his salary go up, but he's saved an additional amount, and that propels him to the other side. So now Edward is at the blue star. So what does this mean? This means that if we ignore causality, of course, we're not going to get optimal results in a world governed by causal laws. Now, in this particular example, there was a positive causal relation between the variables x1 and x2. As you can see, it's a positive 30% of x1 plus whatever. There are cases, of course, where causal relations are negative. One example is, let's say I'm an agriculture firm, and I'm deciding on where to place a rice paddy. I have various elevations. And of course, we know with every 100-meter increase in elevation, we have 1 degree drop Celsius in terms of temperature. If I don't take into account the negative causal relations that exist, what's going to happen? I might give a recommendation that's completely useless. So I think you all get the point here. Counterfactual-based recourse actions from existing methods do not yield optimal and sometimes not even feasible solutions for recourse. But what does feasibility mean specifically? So in the case of the structural causal model framework, feasibility means that we have to perform a do operation on some number of nodes, xi's, within our system. What we do is basically we have to select those nodes, which are bouncing for us over there. We need to select the subset of nodes upon which to act. If we have explanations from existing methods, we have two options to select those nodes. The first one is we either intervene on all of the variables, so I in all of the list of D. And the second one is we only intervene on those variables that the explanation tells us to change. Unfortunately, both of these fail us in this case as well. If we only intervene on a subset of variables, of course, as we saw in the previous example, there are downstream variables which we don't know what the effect of that change will be. If we try to intervene on everything, sometimes we run into situations where we have non-feasible interventions. What's an example? An example is you are a grad student or you are an applicant to become a grad student. You get denied. And the recommendation is, why don't you come back the next year? And at the same time, don't increase your age. That's not possible, right? So if you're forced in the first case to intervene on everything, then you're going to have to employ some non-altering interventions, and that might not be feasible in the real world as well. OK, I'm sure you all now understand that from the previous slide, we said counterfactual-based recourse actions from existing methods do not yield optimal actions for recourse, and now they do not yield feasible actions for recourse. And this gives us our first proposition, which is that counterfactual-based actions from prior works guarantee recourse if and only if the set of descendants of the acted upon variables is the empty set. And that means that we can only, in this particular case, be intervening on x3 among the whole system in order to be giving an actionable recommendation. And for obvious reasons, that should be bad because we're restricting the possible actions that an individual can take. Is it all doom and gloom? Well, I hope not. So one of the first contributions that we had along this line of work was to present an alternative optimization problem which looks almost identical except for the constraint that's highlighted. And what that means is that instead of assuming that features can be acted upon independently as shifts, we now have this rather complicated looking expression of FA, F inverse X, which is really just the abduction action prediction steps that Perl gives us in the causal framework. If we make causal assumptions, then we can explicitly add those assumptions inside the optimization problem, and then try to give recommendations based on that. What does this entail? Or what does this mean for us? This means that instead of assuming rather naively that the world is made up of features that are independent of one another and have no effect on one another, now we can actually model worlds in which they have causal relations between variables. Of course, we need to make those assumptions, but without those assumptions, we're not really going to get anywhere in the first place. Now, someone might put up their hand and say, that's a really scary looking assumption that you've made there. And that constraint assumes that you know everything about the world in terms of causality. And you'd be right. So in follow-up work, we try to loosen this assumption a bit to make it a bit more practical. Let's summarize kind of how far we've gotten so far. So this is the proposition from the previous work, which is to say that prior methods for generating counterfactual-based actions would guarantee recourse only if you're acting on leaf variables in a sense, which is a rather restrictive view. In the follow-up work that we had, we said that ignore everything from the past and just look ahead. What are the conditions under which you can generate recourse? And it turns out that generally, you can only be guaranteeing recourse if the true causal model is known. So the person who put their hand up and said that that's a very scary looking assumption, you'd be right. But unfortunately, we show through an impossibility result that without knowing exactly how causality works in the world, you are unable to guarantee recourse. So what does this mean? We can't give it deterministically. We have to give it probabilistically. Let's just build up some intuition as to how this looks like. So this is Edward again. We have the same decision boundary. We have now an M star, which let's call an oracle model of the world. Had we known, or were we to know how causality works exactly, then the action A would throw Edward on the other side, and that would be the optimal action. But we don't know that. We don't know that. What do? We make further, unfortunately, we make further assumptions. So if we were to assume some alternative models, like M1 and M2 and M3, in this case additive noise models, then perhaps we could say, under the assumption of additive noise models, we'd be able to give probabilistic recourse. Now, the same person might put up their hand and say, I don't want to make this assumption either. I don't want to assume additive noise models. That's also restricted about the world. And I'd say, fine. We can't no longer give individualized recourse, but now we have to give recourse for not just Edward alone, but Edward and similar looking individuals to Edward. In the causal ladder, if you remember, the top level was counterfactual queries. Without making assumptions on the form of the SCM, we take one step down, and now we're down in interventional queries. And of course, the more loose your assumptions, the more loose your uncertainty about what happens to the result of that action that's being performed by Edward. So we present a complement of deterministic recourse, which assumes full knowledge of the SCM of the world, with two probabilistic approaches, both at an individualized level and a subpopulation level. And if you're interested, you can take a picture of this as a summary, but all of this is also online. So to answer the first question then, do counterfactual-based recourse actions from existing methods yield feasible and optimal actions for recourse? No. Instead, you're going to have to reformulate the optimization problem to include causal assumptions, which might then yield deterministic or probabilistic recourse. What about the second question? How does providing recourse affect other stakeholders? Everything we've talked about so far, we've only taken the perspective of Edward. But of course, Edward does not live in a vacuum. There are other stakeholders, such as researchers and developers, owners and deployers, examiners and regulators, and other data subjects, who will be affected by the one recommendation or explanation that we're giving to this individual. And so this is now, I'm going to just present initial strides into open research questions that exist for this topic on the relationship between recourse and robustness, recourse security, privacy, fairness, strategic behavior, and all of that. I'm, again, just going to present the tip of the iceberg because it's very much an open question. So let's consider this case. We have Edward and Edward prime, who are sampled from two distributions of individuals. The distributions are up top. Basically, we're saying that there's a sensitive attribute A. In this case, A could represent whether someone's wearing a tie or not. And then we have the variable X, which is in this case defined as 2 minus A's times some Gaussian distribution. Now, in terms of fairness of prediction, by the way, each individual is just represented with one variable X, and everyone who lies on the positive side of X is given a loan. Let's assume that's the system. That's the system up there. Y is equal to sine of X means that anyone on this side is positively predicted and given the loan. Now, in this particular case, this model turns out to be fair in terms of prediction on these two populations. Why is that? Because half of the light blue population are rejected and half are given loans, and half of the dark blue are rejected and half are also given loans. So it's fair in terms of its prediction. But as can be seen, the distance between these two individuals to the boundary, which is their cost of performing an action to overcome the difficult situation imposed to them by the AI system, is going to be much more for the population in dark blue than it is for the light blue. And so we have this whole rich, thriving literature on AI fairness, in parentheses, for prediction. But what about fairness of recourse? How do we overcome a situation where we think the system is fair, which could fail in many ways in and of itself, but completely ignore the fact that people that don't get the particular resource that they're applying for, like admissions or loans or kindergarten assignments or whatever it is, we're completely ignoring the fact that some people might be treated differently than some others, and that won't be fair. So, of course, there are initial solutions that one might explore, such as restricting the classifier inputs, which is going to cost the institution more, or further constraining the optimization problem, which makes solving the optimization even more difficult, or other representation learning approaches, but unfortunately all of these don't do justice to the good solution that we're looking after. Okay, the complement of this is robust recourse. So now let's say that this is Edward and very similar looking individuals to Edward. So I go to a bank, I fill a form, and by mistake I've filled one of the boxes incorrectly. Put my age as 31 instead of 32. I've made some error in my input space. If I don't account for similar individuals to Edward when I'm giving a recommendation, that might mean that that recommendation completely fails my situation. And so giving non-robust recourse actions would maybe 50% of the time only work when acted upon. But how do we design systems that give us a robust recommendation for recourse? Again, here are some solutions. So basically the question is, how do we safeguard against action against small changes? So one approach is that we change the classifier altogether. So this dotted line is now the classifier. And of course, as you can imagine, this is now costing the bank a bit more. They might not like that idea. We can further constrain the optimization, once again jeopardizing the feasibility of it. But this also bears an interesting question, which is, among the stakeholders that exist, who should bear the cost of recourse? Of course, Edward is going to be performing some actions, but how does this affect other folks? So in this particular case, if we just look at the cost of the individual versus the cost of the institution, non-robust recourse would lie somewhere here. If we were to give robust recourse recommendations, initially that's just going to cost the individual more. Or maybe if we regularize the classifier, it's going to cost both of them a bit more. But there's also another stakeholder here, and that's society, right? Society sometimes provides subsidies to specific groups to make it fair or to make it robust. And so managing this trade-off between the different stakeholders that exist and how much cost each of them has to incur for the task at hand is itself an open question. Okay, I'm going to end with just one other part, or at least end this part with just one other example, which is data and model stealing. All the while, we've been talking about recourse and counterfactual explanations. In this particular case, we have Edward represented now by this red cross. And we know that the closest hypothetical individual to Edward is now this green cross on the other side of the decision boundary. What does every counterfactual explanation reveal to us? It reveals, by definition, that every individual that would lie in this ball is also denied the loan. Let me say that again. Counterfactual explanations identify the nearest point on the other side of the boundary, right? So by definition, any point within a ball where the radius is between the nearest point and the Edward itself will not be on the other side of the boundary. And so they will all be denied the loan. Okay, so what does counterfactual explanations reveal? Each explanation shows a portion of the space that shares the same class as the data point. Now what if your friend is also here? What if you've gone to, I don't know, the ER, and they've given you some recourse recommendation, and you know your classmate also shares, to some extent, your characteristics, and now you've inferred something about your classmate just by receiving one recommendation? Does that mean that we violated that other individual's privacy? How do we manage that? Who says I'm allowed to receive a recommendation if that means that it's going to partially violate someone else's privacy? Now, it gets worse. This is just one explanation. As you start to give more explanations to individuals, it's not just about the privacy of other individuals, but now what we're going to call these factual balls. Together, you're spanning the entire space, and you're able to somehow reconstruct the decision boundary altogether. This is not a fake problem, by the way. 2017, there were models hosted on AWS, and there are approaches with budgets of less than $100, on the order of 1,000 queries, that you can make to these models. You don't have the models themselves, but you can query the models, and then you can approximately reconstruct them with near 99% fidelity. What does that mean? So a company comes along, spends millions of dollars developing something, and you just make some queries. Of course, you have clever ways of making those queries, but with a budget of less than $100, you're able to reconstruct that? Or in this case, with explanations, give 5 explanations, and now you've lost half of your model? How do you deal with that? Of course, you want to give explanations. Sometimes that's required by law, but there's problems with it. So how do you give good explanations? Okay, so yes, the answer to the second part is, how does providing recourse affect other stakeholders? Offering fair and robust group-level recourse requires a delicate balance between the needs of the one and the needs of the many. Let's summarize what we've learned so far. So in general, counterfactual explanations do not imply consequential recommendations for recourse. Recourse can only be guaranteed under perfect causal knowledge, and of course we don't have that, so probabilistic approaches will allow us to relax these causal assumptions. With assumptions, of course, come trade-offs, and there's going to be a trade-off between the strength of those assumptions and the level of individualization when offering recourse. In the second part, we studied the diversity in stakeholder needs, and ultimately, really, the point I want to make is that maybe most of us here are computer scientists. We should definitely not be the ones that are only in the room when addressing these questions, because they go far beyond what we can solve in an optimization problem. I promise that there are laws that require this. This is the Directive on Automated Decision-Making just from last year. Recourse is on the list. So any company employing some form of automated or semi-automated decision-making system is required by law to also give recourse, not only explanations, but recourse itself. So not only understanding why something happened, but giving actions that would help overcome that situation. So happy to chat about this as well afterwards. But let's also talk about what remains to be done. So there are, of course, many open questions that we've alluded to so far, but there's more. We so far have assumed a complicated decision-making problem, which was technically a classification or a regression problem. But what if our system is a scheduling system or a matching system? I've said like kindergarten assignments. Like if you don't get the particular kindergarten that you want for your child, do you have any recourse? They can't come back to you saying there was an algorithm that decided. How do you overcome that situation? Furthermore, we have assumed variables in this case, like bank balance and age, that have meaningful concepts to us. But many times we're working on characteristics of individuals which we might need to infer what those concepts mean. And we might need to learn or abstract those concepts. Of course, we've assumed interactions or actions are just a single-step causal intervention, which itself was very difficult to deal with. But many times you're going to have to take multiple steps in sequence to actually get to a point that you want to get to. So how do you optimize for that? Of course, we talked about these other stakeholders, and we're going to ask, is recourse enough? Do we need to care about fairness, privacy? How do we actually handle that? Is the individual receiving recourse to trust the decision maker or the explanation giver? Like, are these truthful entities within this explanation process? And finally, there's world knowledge that we have not yet been able to capture within the optimization problem, such as for an individual, maybe one individual, it's easy to perform a particular operation versus another person it's not. So how do we build in these individualized constraints or cost functions within the optimization? Okay, I want to end with this slide. It should be obvious to everyone from the examples that we talked about that we're not just talking about Edward and loan approval, but we're talking about all these scenarios where we currently have AI systems making consequential decisions for humans. And it's okay if you feel a bit scared. That means that you understand the urgency. But also, if you're very much interested in solving these open problems, I'm happy to chat. With that, I thank you for your time.
Thank you, Professor Amir, for that awesome talk. We do have about 10 minutes for Q&A, so let's go to the gentleman in white there.
Thank you very much. It was a very interesting talk. I have a request and a question. The request is, you had a slide, I believe it was 25, that you said, this is the very important slide. Take a picture of it, and then 30 seconds later, when everybody just pull out their smartphones, it's gone. Okay. Could you show it again, please?
Let me pull that.
Thank you very much. And then the question that I had was, throughout the talk...
It's like a table. You have a summarization of everything.
There it was. Yes, this is the one.
Yeah.
I really appreciate that. Thank you. The question that I had was, throughout the talk, I think it was going back and forth between individualized and subpopulation recourse and kind of accommodations. My question is, if, first of all, the decision tree that you showed in the beginning, it seems like this is a subpopulation-based kind of recommendation. Maybe I'm misunderstanding this, but in a simple decision tree, basically the outcome is for a subpopulation, right? There are some examples that match those conditions, less than 75,000 income, et cetera, right? So it is targeted towards subpopulation. Now, if recourse is provided to subpopulations, would that change the decision boundary of the bank that is providing the loan, et cetera? My understanding is, okay, you provide a recourse to subpopulation, everybody rushes in to get their loan. The bank now needs to consider that in how do they model risk, et cetera, et cetera. Is that a fair understanding, and is that a problem?
Right, so I'd be happy to address the first part of your question after, but the second part, which I have a straightforward answer for now, is that yes, if the bank in advance is assuming that there will be some strategic behavior gaming from the population that will be receiving recourse, then they might want to in advance make some adjustments to their model. Where do we see this already? We see this in adversarial training, right? The entire field of making adversarial perturbations, this image is this, but it's not really. One way to overcome that is to upfront train the model, and not the instances within the data set, but also randomize instances very close to that. So that would also be one approach to saying, I have no choice but to give recourse to a subpopulation, so what does that subpopulation look like? And how do I adjust my decision boundary in advance for that? The problem is, banks might be hesitant to do that, because that might mean that somewhere else their accuracy drops, right? There's always going to be a trade-off between these desiderata. And so who imposes the fact that you want to be fair in terms of recourse on a subpopulation versus you having less in your bottom line? That's not really a technical question. All we can do is provide maybe a knob to say this is how you control that trade-off. But who determines that? That's not a question we should be answering, I don't think. Yeah.
So the example about Robert was more of a factual decision boundary. So we know that it's at 75,000 and we have a decision tree there. But in the case of LLMs, where there is a probabilistic decision boundary that we estimate the next token in terms of the more likelihood of it being as the next prediction. So how do we apply recourse to that, in that scenario? Because do we connect recourse to, let's say, modifying the prompt engineering or maybe realigning embedding vectors? So how do we apply recourse in that action? So to correct the behavior of LLMs?
Right. I mean, that's a great question. To answer that, just briefly, we already do probabilistic decision boundaries in probabilistic recourse. Technically speaking, what we do is we don't look at just Edward, but we look at Edward under different hypothetical interventions, Monte Carlo, meaning like 100 Edwards. And then we want to move the expectation to the other side, not just the deterministic effect of an action, but the expectation of an action on the subpopulation to that. So in the case of LLMs, what that would be is you don't look at just one prompt. You do multiple beam searches, and then you get multiple results, and then you try to put that to the other side. Make sense?
There's a question there.
Thank you. My question is about the actual, I guess, variables that you're changing when recourse happens. Isn't there, I'm just trying to understand, does this assume that those particular variables are causal in nature? Because in the default loan example, it's a bit more abstract, but typically when you build models, you're trying to predict something, and those variables might not actually have a causal interpretation on your prediction. So if you then try to recommend them as something to change, are you not then assuming that that particular variable is a causal link to what your output is? That's kind of...
Yes. I think the short answer is yes.
Okay. And is there problems with that, I guess, like in the consideration?
So here's the thing. You're right that with the system that we're assuming, I'm going to emphasize and underline assuming, right? With the system we're assuming, we're saying that such and such variable is a cause for such and such other variable. Now, my counter argument to not doing this approach is to say, I'm going to turn a blind eye, and I'm not going to make any assumption. That is still an assumption. That's assuming that that variable is not causing this one, right? We can't shun away from that. We're going to in any case, we're going to make causal assumptions. Even if we don't make it explicit, if you don't make it explicit, that means that you're assuming independence. Is that right? We've already seen cases where that's not right. So the follow-up to this is also that all variables in the world, in these systems, again, we don't talk about this in machine learning often, but all variables are causally related. Always. They might not be one a cause for the other, they might have a common cause. And that's called a hidden confounder that we typically abstract away and turn a blind eye at. But any assumption you make, or lack thereof of an assumption, is going to affect your system, and if that doesn't match the real world, then you're wrong, basically.
I think we have time for one more question, if anyone has one more question.
Okay, well, thanks for
Okay,
coming.
that's everything. Thank you, Professor Amir, Hossein, for this presentation.